In the previous video, we offered proof of concept for a novel idea to restore the functionality of an electric golf cart by replacing the heavy and expensive batteries with a simple generator. The generator device is something we're calling the petroleum battery. Well, because it operates on petroleum and replaces the batteries. So here are some benefits and drawbacks of the petroleum battery. Firstly, the petroleum battery is significantly lighter than the traditional bank of lead-acid batteries, so right away we can see a reduction of the overall weight the golf cart has to carry. Secondly, the recharging time of our petroleum battery can be measured in seconds, and that's because our battery uses commonly available gasoline to create the electricity. And that means recharging can be done off the grid, anywhere, anytime. And thirdly, well, I don't know, but I'm sure there's more than two benefits. Now, here are the drawbacks. When you take a close look at our petroleum battery and analyze it according to the laws of thermodynamics, well, there is a loss of efficiency. However, we don't care because this is a fun project. And finally, depending on the alternator that's being used, well, our petroleum battery may not provide 100% of the current that was available from traditional batteries. But based on some of the testing we've already done, that may not matter. Okay, let's get started with today's episode. Now, today we're going to continue developing and testing the petroleum battery. So in this video, you can look forward to seeing on-the-road and off-road testing, plus high-speed testing. Plus, we're going to attempt to pull a 3,000-pound Chevy truck with our dilapidated golf cart. So stick around, this is going to be fun. So the first thing we need to do is figure out a way to control the petroleum battery with the accelerator pedal on the golf cart. And let me tell you, that ain't easy. First of all, the speed of the engine is not a concern right now. For our testings, we're going to be running the engine at a constant speed between 2,500 and 3,000 RPM. We'll address engine speed control at some point, but today we're going to focus on the throttle for the alternator, which is completely different from the engine throttle. Let's take a look at a diagram and I'll show you what I'm talking about. So this is the rotor that's inside the alternator. In the previous video, we disabled the voltage regulator and connected a pair of 12-gauge wires directly to the brushes. These two wires will supply voltage and current to the rotor in order to vary the magnetic field that the rotor creates. We don't expect these wires to carry more than 8 amps, and 12-gauge wires should be sufficient. Now, in the previous video, we directly connected the variable DC to DC PWM power supply to these wires, and we were able to throttle the alternator by turning this knob. As you can see, we have excellent control of the DC motor that drives the rear axle, and that's because we're dual-purposing the alternator as both an electrical generator and a DC motor controller. Now today, we have to figure out a way to connect this knob to the accelerator pedal on the golf cart before we can do stupid things to the golf cart and see if the petroleum battery will hold up to our abuse. I reckon if we damage something in the petroleum battery, we'll still be making progress. So in order to proceed, we first need to see what this knob is connected to inside the power supply so we can come up with a plan. Now, the power supply that we're using is available on the Jungle site for about 12 to 14 bucks. It has an input voltage that ranges between 7 and 70 volts, so it'll work fine with our little 12-volt battery. It's hard to believe, but this little guy can supply up to 30 amps on the output. We expect not to need any more than 8 amps, so this is perfect for our application. It's cheap and it'll give us the power we're looking for. So what's inside this thing, you may ask? And that's a good question. Now, to my nuts and bolts audience, I'm going to get a little nerdy and talk about electronics for a moment or two. I don't expect a lot of folks to fully comprehend everything, but just be patient and hang in there. Well, if we take a close look at the circuit board, we discover that this gizmo uses a 555 timer configured in a PWM signal circuit. This is absolutely fascinating to find a 555 out in the wild 25 years into this century. You know, I was expecting a microprocessor of some sort, but instead I found a circuit from Forrest Mims' Engineer's Handbook from 1983. Anyway, this is the front end of the circuit, and this potentiometer is represented here. I measured the resistance across the potentiometer, and it was 100,000 ohms, which can also be expressed as 100 kiloohms. The point in looking at this schematic is, this 100 kiloohm potentiometer is part of an RC circuit, RC meaning resistor capacitor, and it's a timing circuit and not a conventional voltage divider. So what that means is, we can't substitute a potentiometer of a different value without re-engineering the entire circuit. Now, for some of the audience, modifying the circuit is not a problem. However, for the overwhelming majority of the people watching this video, modifying a circuit board built with surface mount components that are smaller than a grain of rice is not something they want to do, nor can they do without the proper tools and knowledge. The bottom line is, the value of this 100,000 ohm potentiometer must remain the same, and we can't substitute a 2K or a 10K potentiometer and expect the circuit to function as designed. Now, as a side note, off camera I already tried that, and let's just say the results were not good. Anyway, keep in mind this project is intended to be relatable and understandable by people without an electronics background, so we need to keep it simple. Now, I'm not sure everybody understood the significance of the 100,000 ohm mandate that we have to work with, so I'll help you out. This drive-by-wire throttle pedal assembly that I believe is from a Chevy Cobalt would be perfect for our project. However, the potentiometer that's inside this device is about 3,000 ohms, which is 97,000 ohms less than what we really need, so it won't work. This 5,000 ohm linear position sensor would also be ideal, but again, this device is 95,000 ohms less than what we need. My point is, everything that is both affordable and commonly available will also likely be in the 2,000 to 5,000 ohm range. So, we're going to have to custom build a throttle with a 100,000 kiloohm potentiometer of some sort. Now, a standard rotary potentiometer typically has a range of motion of 270 degrees, which is a lot of movement. Ideally, we would want to have something with 90 degrees or less of movement for a simple throttle. So for now, let's avoid using a rotary potentiometer. Now, a linear slide potentiometer like this one only has to move a short distance, so it's a logical choice. However, keep in mind, this thing is extremely fragile and we'll have to construct a complex series of linkages to make it work. Now, whether we use an off-the-shelf linear slide or rotary potentiometer, we have to remember that neither device was engineered for constant movement that's seen on a throttle. So, it's likely that both types of potentiometers will wear out sooner than expected. The best choice is, of course, to use the throttle position sensor from a car, but like I mentioned earlier, something like that is about 2,000 ohms, and we need 100,000 ohms, so a throttle position sensor is out of the question. So I reckon we have a huge problem. The good news is, today we have a workable solution. Now, this is not ideal, and it's far too complex for a normal human to construct, but I'm not a normal human. The good news is, I'm also working on 2 other designs that are much simpler, but it takes time to develop things off camera. Now, this guy is built from no less than 9 custom engineered 3D printed parts, and it has 3 bearings in it to reduce friction and binding. It's way too complex. I understand that, and I'll provide a simpler solution in a future video, but this is what we have to work with today. So even though this is not the final design, I want to walk you through some key points that had to be considered. So this is the linear slide potentiometer that we're using, and it's extremely fragile. It wouldn't take much to destroy it. So I buried it inside this 3D printed housing. Now that solved some of the problem, however the 3D parts ain't exactly strong either, so I also had to fabricate some hard stops to limit the amount of movement. That way we wouldn't damage any of the 3D printed parts. These aluminum hard stops will prevent anything from moving beyond the limits of the fragile parts, and at this point I believe the crappy linear potentiometer is safe. Now, this gizmo assumes that there is a throttle cable in the golf cart, and that's quite an assumption because this cart doesn't have a throttle cable. So meh, this is the best part of working on something you don't care about. Just flip it on its side and it'll be fine. Trust me, this cart can't get any worse. Well, maybe it can. So the point in tipping this thing over is so I can rig a throttle cable to this accelerator pedal, and I'd rather not do this while laying on my back underneath this buggy. So the plan is to connect the cable to this thing with a custom bracket. Fast forward a few minutes and we have the throttle cable connected to the accelerator pedal. Not really much to see here, other than it would be a lot harder if I didn't tip the cart over. Anyway, the cable's routed into the battery compartment and we're good to go, so let's continue. Fast forward again, and we have the throttle for the alternator connected to the accelerator pedal on the golf cart. This system will be replaced as soon as I get the simpler version finished. The potentiometer that came with this power supply was removed, and I went ahead and soldered 3 wires to the back side of the circuit board so we can connect this thing to the alternator throttle. And because I can't help myself, I hot glued the wires in place because, well, it's the right thing to do. Anyway, as you can see, the throttle cable is connected to the gizmo, and if I press down on the accelerator, we have the world's first foot-controlled alternator throttle for a 1967 Cushman electric golf cart with a petroleum battery. Wow, those words were never spoken before in the history of the human race, and I'm glad I can finally say them. So if I zoom in, you can get a better idea how complex this thing is. The good news is, it works, and today we can gather some preliminary performance data on the petroleum battery. But first, I want to talk about safety. The system we just built is extremely dangerous, despite the fact that I tried my best to make it safe. You know, if the linear slide potentiometer fails, well, that would cause the power supply to full field the alternator, and that's what we call a runaway condition. The good news is, well, a sudden full field of the alternator would likely stall the little engine, and the situation would be contained. However, in the event we lose control of this contraption and the engine doesn't stall, well, that would be bad. So I installed an emergency stop switch to disconnect the power supply from the alternator. The e-stop switch is definitely good, but I also rigged another switch that's connected to the brakes, and pressing down on the brake pedal will also cut the feed to the alternator via a relay. The brake switch and the e-stop switch add a bit of complexity to the system, but they're necessary evils. Now, before we start doing stupid stuff to this golf cart, let's go ahead and do some calculations and mathematically figure out how fast this thing should be able to go. I reckon the first thing we need to do is figure out what the gear ratio is on the rear axle. And what I learned from a quick search on the internet is the gear ratio can vary on these things. So in order to determine what the actual ratio is, we have to do an experiment and count how many revolutions the electric motor will make for this wheel to spin 1 revolution. As you can see, we've painted a line on the tire so we have a reference mark, and all we have to do is push the cart and count how many times this flange spins for the wheel to make 1 revolution. Sound simple? Well, let's find out. Alright, that's 1 revolution. Let's keep going. And it looks like the motor made 12.7 revolutions, so that means the cart has a 12.7 to 1 rear axle ratio. Wow, the motor had to spin almost 13 times for the cart to move from here to here. Now that's a lot of revolutions and not a lot of distance covered. So this big DC motor is rated at 3 horsepower at 3,000 RPM and 4 horsepower at 4,000 RPM. Now I'm not sure what the maximum RPMs are for this motor, but let's figure it's in the 4,000 range. Alright, let's do some math with this vehicle speed calculator. Over here we plug in the rear axle ratio, which is 12.7. Next is the height of the rear tire, which is about 17.25 inches. And right here, let's put in 3,000 RPM. Since the motor is directly connected to the rear axle, we can use 1 here to indicate the ratio between the motor and the axle is 1 to 1. Then we can click on Calculate. So with the electric motor at 3,000 RPM, this cart will go 12.13 miles per hour. Now that's pretty slow. Let's try this again, and this time we'll use 4,000 RPM and see what the extra 1,000 RPM will get us. And calculate. Just over 16 miles per hour. That's better, but it ain't great. So last week when we road tested this contraption, we briefly saw 15 miles per hour on the speedometer, and it looks like we were generating about 36 volts at the time. Very interesting. Now I'm not sure what the upper limit of the alternator is, but if we can generate 48 volts, well, we might be able to pick up some extra speed, but we will definitely be voiding the warranty on everything you see in this picture. Actually, I'm not familiar with what happens when you overspeed an electric motor, other than possibly overheating it. If we have any experts in the audience, feel free to put it in the comments because I'm sure a lot of people would like to know. Alright, well, now I feel like having some fun, so let's power up the petroleum battery and go for a spin. Activating the petroleum battery requires pulling on this rope once or twice. We do have an electric start version in the works, but right now it's not high on the priority list. Since the last video, we went ahead and fixed the exhaust leak, but this thing is still noisy from all the vibrations. At some point, we'll try mounting the petroleum battery on rubber isolation bushings, and that really should help with the noise. Off camera, we loosely installed the seat and we're ready to go for a ride. Now if you look closely, you can see that the emergency stop switch is within easy reach of the driver. We also had to double up on the return springs for the alternator throttle, and that makes the foot throttle a lot harder to press now. Alright, we're moving. Now today, I'm able to operate the throttle by foot, so I'm in full control of the vehicle. I also have a cameraman on board, so this cart is hauling 2 adults. Now on the grass, the petroleum battery doesn't seem to have any problems moving the cart, but my yard is a bit bumpy and I'm concerned about stuff bouncing around, so we're going to have to take it easy. Let's do a brake test and confirm that we can disable the throttle in an emergency. And as you can see, the throttle is really stiff. Now once I get the cart moving, I'll press on the brakes and that'll kick in a relay that'll disconnect the alternator from the accelerator pedal. And it works. The off-road testing wasn't very thorough because of the bumps in the yard, so we're going to pull this 3,000-pound Chevy truck to simulate going up a steep hill. Normally this truck takes 2 people to push, so this should be a good test. Now at this point, I have the accelerator floored and unfortunately I don't have any gauges hooked up today, but I reckon we're pushing the limits of the 140 amp alternator. So, we were able to pull this truck, but I feel like the petroleum battery was pretty much maxed out. I'm not sure how I feel about this, especially since I had the throttle for the engine maxed out as well. Now I do have some permanent gauges on order, and in the future we can see how much current we're drawing from the alternator. The good news is, well, the alternator survived this test. Let's take this out on the street and see how fast it'll go. Yeah, the accelerator is really stiff with the double return springs. Now, according to the math, top speed should be close to 16 miles per hour. Oh, it looks like we exceeded that already. Okay, so much for the math. This is interesting. You know, this thing hauls ass, and if we can bring the noise down, it would make an excellent street cruiser. So in this little town, I can get a permit to drive this thing on the streets legally. A lot of folks around here use these things to get around, and it seems like it would be a lot of fun. Wow, 21 miles an hour. That's got to be a world's record in something like this. Now, if you listen closely, occasionally you can hear the engine struggle, and that's because I'm playing around with the engine throttle. During acceleration, well, the engine wants to be spinning real fast, but at cruising speed I can pull back on the engine throttle a little bit. Overall, it seems like the engine's happier when it's spinning faster. So 21 miles an hour means the big DC motor was spinning at 5,200 RPM and the gasoline engine was likely spinning at 3,600 RPM. So there's quite a bit of an overdrive at full throttle. And we're back. Today it was in the mid 60s and the breeze we were getting at high speeds was really nice. Not too shabby. This thing hauled 2 adults around no problem, although we do need to work on the noise. Let's see how hot stuff got. Well, the exhaust is hot. I guess that makes sense. The alternator, well, it's warm, but not really hot. Yeah, I'd say the case is about 100 degrees Fahrenheit, which I'm sure some of the heat is from the exhaust system. Now in the back where the diodes are, well, that's actually not hot at all. I really need to put a temperature probe back here, but for now, it would appear that the alternator has survived. Now the double springs on this thing is way too much, and it makes the accelerator difficult to use. I reckon at some point, this Ruth Goldberg throttle will get sent to one of my patrons. It would definitely make interesting wall art with a fascinating story behind it. So the first real road test actually went extremely well when you consider the golf cart carried 2 adults down the road without any issues. You know, from what I read in the comments, a lot of people wondered if something like this would actually work, including myself, and that's why I tried it. I think due to the inherent losses in the system, the people that are smart enough to put something like this together just wouldn't do it because the basic math says it's a bad idea. Now, just to be clear, this system is not the same as what you'd find in a Toyota Prius or Chevy Volt. Those cars and other hybrids use a more complex eCVT system. Now, there are plenty of videos on YouTube that explain how the Toyota Prius eCVT system works, so I won't get into that. But as I mentioned in the previous video, the system that we're using is modeled after the diesel-electric drive in a locomotive. Now, regardless of the efficiency issue, I find it fascinating that this actually works as well as it does, but we are far from being done. In this video, well, I had hoped to get more finished, but building a workable and safe throttle for the alternator absorbed way too much of my time. You know, trying to make this project simple is ironically extremely difficult to do. All the challenges that are slowing me down could have been eliminated by using an Arduino microcomputer and a few dozen lines of code. However, the challenge is to continue to make this project simple, but once everything is sorted out, I will do an Arduino version, and you can count on that. Just a reminder, the goal of this project is to see if it's possible to replace the batteries on a dilapidated electric golf cart with an alternative power source. We chose to reanimate this old and forgotten hulk because this cart was basically on its way to the scrapyard due to the entire electrical system being both outdated and damaged. Now, it's possible to use the petroleum battery in other applications. For instance, if our golf cart were more complete, well, we could have built an onboard range extender system that would charge the batteries off the grid. I think that would be a fun project as well. Now, unfortunately, for something like that, we would have to buy a complete and fully functional golf cart. Meh, right now, that just ain't in the budget. And we certainly aren't going to dump any real money into this heap. Nope. I'm afraid this cart is only good for prototyping and experimenting with the standalone petroleum battery system. However, I am on the lookout for another reasonably priced 4-wheel golf cart in the Wichita, Kansas area. So ultimately, this is a small engine channel, and our projects always involve a small engine. I personally have zero interest in anything full electric. Stuff like that is for other channels to explore. Doing fun projects with small gasoline and diesel engines is what we do best. Anyway, I had fun today, and I hope you did as well. We'll see you next time. Until then.